So, do we have any additional questions?
I wanted to know what some of the reagents from exam one you think will be most likely to show up on the final. Like you had a
Reagents
lot
from
of
exam one.
yeah, like I remember when we were doing office hours for exam one, you said like a lot of it was just from Orgo one, and you had like some basically like a small list of like 4 or 5 reagents that were like extremely important for that test.
Yeah, so here's the thing. I I can't tell you the reagents to know for organic one, especially with that reagents list that he's going to be asking for.
Sure.
Because he's going to choose a random number generator, right? Like these are going to come out of the blue at you. So, um if I told you to focus on certain ones versus other ones, then I'd be doing you a disservice because I don't actually know. I do think there are some that are more important than others, but based off how this test is going to be formatted, that doesn't really matter because, you know, we've used SOCl2 in this class way more than we've used sodium acetate. But, when you get to that question, you have just as good of a chance as SOCl2 and sodium acetate popping up on the test. So, um, I think prioritizing for those kind of questions is hard. I will say for like the fill in the blank, like you've seen that he tends to like he likes his H2 palladiums and D2 palladiums, right? You see that come up often. We haven't seen it in immediate, but he does like his ozonolysis questions, so those tend to pop up. Um, you've got to always be aware of Grignards. Grignards the most important reaction organic too, if you ask me. So, those are going to come up. You'll probably see a Grignard. Um, yeah, yeah, epoxides. That's one that he does often for the fill in the blank. But yeah, in general, if you are doing the flashcards like I suggested of these, where essentially what I would suggest you do is have a flashcard of 100 of these, and honestly, you guys should get together and like make just one Quizlet or something because you don't need everybody doesn't need to go through the effort of making their own flashcards and like share that Quizlet with everybody and then try to study it. So like you get, something pop up, HCN or something, and you're like, so you see it, then try off memory to be like, I think I'm going to use HCN to do an acidic opening of an epoxide. So I'm going to do this. And you would draw it out and draw it out on a sheet of paper and then flip it over and check to see if that's, the same reaction. But make sure that you're writing things down before you check your work. Just the process of trying to write it from memory instead of just looking at the answers will be very helpful. So that's how I'd suggest you would study for those. But yeah, I couldn't tell you necessarily that anything is going to be more important. Like, because I would have told you that you're never going to see a Simmons Smith again, right? But on the last test, a Simmons Smith popped up, so you never really know.
Thank you.
Yeah,
Do you think that the frost cycle is going to show up on the final?
I would be prepared for a frost cycle. So frost cycles. Quick review. If I gave you some ring, right, and I said, is this aromatic or not? Draw a frost cycle. So I'm gonna actually draw it like this. So he'll give it to you like this. He'll be like, draw a frost cycle to determine if this is aromatic or not. So step one, turn this molecule so one of its points are down, right? Doesn't matter what point, just one of them has to be down. Step 2. We're going to, everywhere there's an atom, we're going to replace it with a little dash. So you end up getting 6 little dashes. And hopefully it's prettier than what I've drawn. Right? So notice how now I've got a dash for each one of these. Then I've got to count how many, pi electrons there are, right? So pi electrons come in 2 forms. They're either lone pairs or double bonds. Essentially, if there's double bond in there, it's always going to be a pi electron. So that's 2, 4, 6 pi electrons. Then I've got to decide, I know this nitrogen has a lone pair, right? But the question is this lone pair up in the pi system or not? So the way I decide that is, he called them pyridines or pyrimidine nitrogens. Really the easiest way to tell is, look at it. If this is sp3, that means it's flat, right? Right. If it's got a double bond attached to it, that means that this is flat out of the page, so it's not up in the pi system. So this would not count. So I end up getting 2, 4, 6. Let's see, there might be a better way to draw these. But I don't actually know if there's.
On the arrows tab, it had a half arrow on there, I think.
Yeah. Problem with this is it's going to be. Oh, I can do this. Yeah, there we go. Beautiful. Right. So 2, 4, 6. Make sure that you populate the lowest one first, and then I would go 3, 4, 5, 6 until I ran out of pi electrons. Then I have, my separator, bonding electrons, anti-bonding electrons, non-bonding electrons. And so that's it, right? Just a refresher. I would go back and look at those old tests, see if you can do them. This again should be pretty easy points. The tricky bit is understanding that, like, that lone pair doesn't count, but in something like this, this guy's got a lone pair that does, right? This is a parole type nitrogen. It's an sp3. There's no double bond attached to it, so he's kind of up interacting with these double bonds. So this would also have, 6 pi electrons, and it would look something like that. Oh, no, like that. Where I would fill all these bottom levels. And it could get trickier than that. Like you could throw multiple nitrogens in there and whatever, but those are frost cycles. I would be prepared for them.
Okay, thank you.
All right, electron counting. Got a question for that. All right, so man, this is a throwback. So you're gonna have some metal, right? And it's gonna be attached to a bunch of different things. So I don't know. It's gonna be attached to 3, 4, 5 different things. So if I remember correctly, this has been a minute. You have to check the atomic number of the metal, right? So actually, for this one, let's go see if we can find an example question from his stuff. Would this have been exam 1? Yeah. Okay. So, number of valence electronies on metal, that's supposed to say electrons. So that's coming from rutheniums from the periodic table. So again, you have to check rutheniums where ruthenium lives on the periodic table. Periodic table. Let's see. All right, so here's periodic table. Ruthenium's 1, 2, 3, 4, 5, 6, 7, 8, right? So that's where we get 8 from. Number of monoanionic ligands. We'll come back to this. Number of electrons from all ligands. So that's these bonds. So there's 2 electrons in each bond. So 2, 4, 6, 8, 10, 12. That's where this 12 comes from. And then the number of monoanionic ligands. So anion means -1. So that's why we're subtracting this number. So the way that I think about this is if you were to take the electrons from the bond, right? If you were to say these electrons shared between ruthenium and oxygen, I'm going to put just onto this oxygen. What is the result from that? I have oxygen bound to something else, and then it now has gained electrons, right? It only has 1 bond on it now. How many bonds does oxygen want to have?
Two.
Wants to have 2. It's low in bonds. It's not sharing enough electrons, so it's actually going to be negative when you put those electrons back on it. So this would count, this would be 1 monoanionic ligand, right? Because when I put those electrons on it, it's negatively charged. If I look at this oxygen, when I put those electrons on it, how many bonds does that oxygen have? I mean, it has 2, so this is neutral, right? This oxygen's happy. So you can have 2 different oxygens. One's negative, one's a anionic ligand, one's not, right? So nitrogen, if I put electrons back on it, I'm going to get a nitrogen with a lone pair with 3 things bound to it. How many things does nitrogen want to be bound to?
3.
3, so it's neutral, right? So this is good. This bromine, if I put those electrons back on it, now bromine, that bromine's not attached to anything else. How many things does bromine want to have? How many bonds does bromine want to have?
1.
1. So this is a bond short, so it's negative, right? So if you forget, carbon wants 4 bonds and no lone pairs. Nitrogen 1 over on the periodic table, right? Nitrogen 1 over on the periodic table. Wants 3 bonds and 1 lone pair. Oxygen wants 2 bonds and 2 lone pairs. And any sort of halogen wants 1 bond and 3 lone pairs. So it's not happy. It doesn't have 1 bond. All right. CN. All right. So CN and CO are a little tricky because you have to know what they look like. CN looks like this, right? So if I put these electrons back onto this carbon, this nitrogen's neutral, but this carbon has 1, 2, 3 bonds and it wants 4. So this carbon's negative, right? So I've got 1 negative, 2 negative, 3 negative ligands. This CO is the same thing. But what's funny about the CO is This carbon is one bond short, so it's negative, but this oxygen has one too many bonds, so it's positive. So this is actually neutral. It's not a negative. It's not an anion. So the upshot of all of this is, like if oxygen only has one bond outside of the bond to the metal, it's going to be an anion. You know, you have to look at how many bonds these things want to have. This is CO is going to be a neutral ligand every time. You know, the cyano group CN is going to be a negative ligand every time. Depending on what's on the bromine and the nitrogen and the oxygen, they can change. So, in this case, I see 1, 2, 3 monoanionic ligands. That's this. That gives me my 3 to subtract from. So 8 minus 3 plus 12 is 17. Do you guys have questions about that? This is actually a really good question because I think it shows you the range of, like, you can't just say everything with an oxygen is negative. But it also shows that sometimes this CN is always going to be negative. The CO is always going to be neutral. So it kind of shows you a good range of them. Do you guys have questions about that?
Kevin, if there was like, for like a different example, if there was like an overall charge on the like molecule, would that go into any of the boxes, or would that be like another separate, or
Yeah, so like if it was like ruthenium 2 plus,
yeah.
yeah, I believe at that point you would subtract 2 from this number.
Okay, thank you.
All right, any other questions? Yeah, I mean, if I'm gonna be honest with you guys, how I would direct my studying, it would be to make those flashcards or share them with as many people as you can, because you really, as soon as one person makes them, like, just share them with as many people as you can. You can just Google these reactions and just copy and paste those images onto a Quizlet or something. You can literally just like type in to Google some of the reaction conditions. And try to use those pictures. If not, hopefully someone has like ChemDraw or you have access to it. You probably had to use it for your lab section if someone took that. So hopefully you guys can make that. But yeah, share it on the group me. Be a nice person. So I would study those reagents, get those free points, study the mechanisms. I would just restudy the ones that you had already studied for test 1, 2, 3, and 4. Hopefully you studied about half of them for each test. So to kind of cover all your bases, so that should come in handy. You're just reminding yourself of what you studied before. And then when you have those two, if you've gotten pretty comfortable with the reagents, then you know the last thing to do is to practice NMR questions and practice synthesis problems. I made a worksheet that I put on Canvas. So if you're struggling with the synthesis problems, let me kind of look at it. So like it's this long worksheet I have. It's I think 11 pages. So depending on where you feel comfortable, you get started at the beginning, right? These are just little mini synthesis. I call that. This is kind of Curly's, Dr. Curly's notation, but essentially you're not adding any carbon-carbon bonds here. You're just turning one thing to another thing. And I'll go ahead and tell you that, you know, doing this is, you're going to be pretty comfortable doing this stuff from memorizing all the reagents from the list. So this is pretty ticky-tacky stuff, right? You know, this is organic 1 stuff. Right, adding HBr across the double bond, and then you can turn this into, you know, a Grignard down the road or something. Pretty useful thing to know. But then you get into like the real reaction, and to me, the fundamental part of organic 2 is understanding Grignards. Grignards are the most useful reaction. It helps you build these longer chains, right? So here we had 3 carbon chains to 3 carbon chains, right? So nothing was changing about how many carbons we had. But now with the Grignard, you're able to kind of start building these longer chains, right? How can I put this together with this to get this? So it kind of starts with simpler compounds, right? This is a little bit easier than some of the stuff you saw in your last test. And it gradually makes them harder, right? It opens up this idea of epoxides. Then it forces you to choose, should I add to an epoxide or a carbonyl? And then some practice using CO2 to make a couple molecules, and then turning those into esters, right? So so this is all stuff we've done. A little Wittig practice, probably not going to be the most useful thing, but it exists. And then some enolate stuff. So you know, enolate with an alkyl bromide, and then, you know, aldol reactions, what they look like in a synthesis. So just tons of practice here. I have an answer sheet put up here. If you're confused about the kind of the format of this, you can email me. I've put the answer sheet here. Oh, not here. I've made a lot of announcements. I put the answer sheet here. So you can kind of work and check your work and kind of come back to this and keep practicing. I would suggest that you kind of skip to wherever you feel comfortable. If you're like, man, Grignards are boring, I can do these all day. Maybe skip down here and do a couple of these problems. Maybe skip down to, you know, benzene, adding benzene to different parts of, you know, adding multiple things to a benzene ring. Get some practice doing that, right? So based off what he posted, these 2 questions here on page 10 are going to be kind of similar to what you might do on a test. So yeah, if you guys have any questions about synthesis, I was planning on talking about synthesis, but you guys had so many questions that I didn't really get to talk about it that much. But it sounds like, based off the questions you guys had about synthesis, that you're getting there. You're understanding on some level. If not, I would start at the beginning of this and see like what happens when I react with a Grignard with a carbonyl. How does that make something that's useful? So practice one of these problems, go back and check what answer I have and how it's different. Yeah. Do you guys have any questions about any of that? Or maybe suggestions to other people about what you're doing to study that I didn't cover that might be helpful? No? You guys feel like that covers it? I got to chat. All right. Well, I'm gonna head off. I appreciate you guys showing up. I hope that was helpful. I'll put at least the last 20 minutes of this video up on YouTube and post the announcements. I'll be happy to answer any other questions if you email me. Good luck tomorrow or Wednesday. You guys are gonna kill it. Yeah. See you guys.
Thank you.
Thank you.